So the next topic we are talking about now is relations. Relations is an interesting topic in math. It also has some practical application in the field of databases. We're not going to see any of that practical stuff, but we're going to do theoretical stuff as usual. So what is a relation? So this is the definition. Given a set A relation on A is a subset of A cross A. So what is A cross A? Remember, this is from the first week or two of the semester, where we talked about one of the operations. One of the set operations is Cartesian product, right? So this is A cross A. This means the set of all ordered pairs whose first item is A and second item is also, whose first item is from A and second item is also from A. All right, so anyways, that was A cross A, the Cartesian product of A cross A. So any subset of that is called a relation on A. Let's see an example. Well, for that, often a relation represents a familiar relationship among the elements of A. So that's often a reason, that's often a justification for why we are interested in relations, because relations help us represent familiar relationships among elements. So we'll see examples of what I mean by that. So first, here's a relation. So first we start with a set, because every relation is a relation on a set. So here's our set. Let A equal 1, 4, 1, 2, 4. And let R be this. Oops, sorry, this should be a 3, not a 4. Hold on. All right, so A has 1, 2, and 3. And let R be the set. So this is a set of ordered pairs. So 1, 1 is one ordered pair, 2, 1 is another, and so on. So there are 1, 2, 3, 4, 5, 6 ordered pairs in this set in R. And now R is not the same thing as A cross A in this case, but R is going to be a relation. So notice R is a subset of A cross A. So A cross A is the set of all possible ordered pairs made from the elements of A. Right? So this doesn't include all possibilities. For example, we don't have the ordered pair 1, 3. Right? That's not in R. But R is at least a subset of A cross A. Right? It's a subset of A cross A. Every element of R is also an element of A cross A. Therefore, R is considered to be a relation on A. Okay, R is a relation on A. That's it. That's the definition. That's just a very simple example of the definition of relation. Now, we can point out that the ordered pair 2, 1 is an element of R, right? It's right here. So we can write this as follows. We often write this like this. This can be written as 2R1. And the way you say this is, you can say 2 is related to 1, or if you want to be more precise, you can say 2 is R related to 1, meaning it's related to 1 with the R relation. But the point is, there's this ordered pair 2, 1, which is an element of R, so we write it like this. On the other hand, the ordered pair 1, 2 is not an element of R. Right? If you look in this set here, you will not find the pair 1, 2. You'll see 2, 1, but not 1, 2. So we can write this as 1 not R2, meaning 1 is not related to 2. But notice 2 is related to 1, so it's a little confusing, because usually when you're talking about people, if A is related to person A is related to person B, then person B is also related to person A, usually. But here it doesn't work like that, right? It's not necessarily the case. Just because 2 is related to 1 doesn't mean 1 is related to 2. Okay. Now let's just point out, let's think about actually, what does this relationship represent? What idea does this relationship represent? Does this relation represent? So R actually represents the greater than or equal to relationship among the elements of A. Let's see. So 1 is greater than or equal to 1. but 1 is not greater than or equal to anything else. So we don't have 1, 2. We don't have 1, 3 because 1 is not greater than or equal to 2 or 3. 2 is greater than or equal to 1. 2 is greater than or equal to 2, but we don't have 2, 3 because 2 is not greater than or equal to 3. Then we have 3, 1 because 3 is greater than or equal to 1. 3 is greater than or equal to 2, and 3 is greater than or equal to 3. So R represents the relationship of greater than or equal to among the elements of A. Right? These are the elements of A. So among those elements, we can represent this relationship with R. In other words, X is related to Y if and only if X is greater than or equal to Y. Remember, so what does this mean? What does if and only if mean? What it means is as follows. If X are Y, that means that X is greater than or equal to Y. And conversely, if X is greater than or equal to Y, then we know that X is related to Y. Okay, let's just maybe clarify this notation over here again. So when we say X, R, Y, which we read, technically we should read it as X is R related to Y, meaning it's related to Y with this R relation. What that means is that X, Y, the pair, ordered pair X, Y is an element of R. That's what it means. And conversely, and on the other hand, rather, X not RY, which we should really read as X is not R related to Y. What that means is that the pair X, Y is not an element of R. So that's just a little bit of notation. All right, now it is often helpful to draw a diagram of a relation. Let's see an example. So here's the same relation that we had in the previous example, right? The same set A and the same relation R. Notice, by the way, R is a set, and it's also a relation. Okay, every relation is also a set. All right, now here let's draw a diagram of this relation R. So this relation is represented by the following diagram, and here it is. So notice what we have here. So we have 3 what I'd call nodes, these little these circles, right? So there's 1 for each element of A. So there's 1, 2, and 3 for the 3 elements of A. Then what we do is as follows. We represent an ordered pair. So let's say there's an ordered pair 1, 1. We represent that by drawing an arrow from 1 to 1. There's an ordered pair 2, 1. So we represent that by drawing an arrow from 2 to 1, and so on. Okay, so putting that all together, we get this diagram, right? So let's say 3, 2. So we draw an arrow from 3 to 2, not from 2 to 3, because there is no ordered pair 2, 3, right? There is no 2, 3. There is a 3, 2. So we draw an arrow from 3 to 2, specifically in that direction. So notice that we draw a node, or you can call it a vertex. Each of these is a vertex. We draw a node for every element of A. So again, this is a node. This is a node. This is a node. They're also called vertexes or vertices. Singular is vertex. So we draw a node or vertex for every element of A, and then we draw an arrow from X to Y. So let's say from 2 to 1, whenever X, Y is an element of R. Right, so if we have a node here and a node here, we draw an arrow from this node to this node to represent that 2, 1 is an element of the relation. Let's see another example of a relation. So let's say we have a set B, containing 0, 1, 2, 3, 4, and 5. And let C be this following set, which has 4 ordered pairs in it. Notice that C is a subset of B cross B, right? Every element of C is an ordered pair made using the elements of B. Now, of course, C is not the entire Cartesian product, it's just a subset of it, but okay. But the point is C is a subset of B. Sorry, is a subset of B cross B. So therefore, C is a relation on B. That's just following the definition of relation. Here's a diagram of C. So here we have, notice we have all 6 nodes, all 6 elements of B written out, okay? And then we want to represent the relation. So we have this ordered pair 0, 2. So we draw an arrow from 0 to 2. We have another ordered pair 2, 0. So we draw an arrow from 2 to 0. We have another ordered pair 5, 5. So we draw an arrow from 5 to itself, from 5 to 5. And then we have another ordered pair 4, 1. So we draw an arrow from 4 to 1. Notice this node here, this 3 doesn't have any arrows connected to it. That's fine. We still have to draw it because it's still part of this set. And remember, C is a relation on B, is a relation on this set. Here's another example of a relation. So the two previous examples were dealing with relations on small finite sets. But we can also have a relation on infinite sets. In fact, that's very common to talk about relations on infinite sets. So Z is an infinite set. Yes, Z is an infinite set. Now we can talk about a relation, we can talk about the following relation R. So consider the following set R, which is the set of all ordered pairs x, y, such that x is an element of Z. So in other words, you have the ordered pair 1, 1, 2, 2, 3, 3. Also, you have 0, 0. Also, the ordered pair -1, -1, and so on. Right. So it's the set of all ordered pairs x, x, such that x is an element of Z. Now, R, this set R, is a subset of Z cross Z. So Z cross Z includes all possible ordered pairs made from integers, right? So like 2, 1, 1, 2, and so on and so on. But R is a subset of Z cross Z. So therefore, R is a relation on Z. Now we cannot draw a picture of this relation because the picture would have to have an infinite size, right? It would have, because it includes an infinite number of elements. But I just want to point out, for this relation, for example, 3R3. That's true. 3 is related to 3 because we have an ordered pair 3, 3 because x, x, right? It's in this case 3 and then 3, 3 such that x, x such that x is an element of Z. That includes the ordered pair 3, 3. Also, -3 is related to -3. But 3 is not related to -3, again, for this particular relation. And -3 is not related to 3. Now, what does R represent? So if you think about it, R represents the equal sign, the equality on the set of integers. So in other words, R is a way of representing equals without actually writing equals. Because R is all ordered pairs made up of integers where the first item in each pair equals the second item in each pair, right? So in other words, you have a pair like 3, 3. You have a pair like -3, -3. You have also 4, 4. You have 5, 5. It represents equality on the set of integers. In other words, x is related to y if and only if x is equal to y. Okay, I just rewrote this set a little bit more clearly. Oops, made a mistake. So the set is the set R has -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and then to infinity in each direction. So you can see that R represents equality, right? And you can, x is related to y. In other words, you have an ordered pair. Every ordered pair means that x equals y, that the first thing in the pair equals the second thing in the pair. All right,